Okay, last lesson of bonding. We are going to talk about mechanical properties of solids, and we're going to talk a little bit about three-dimensional shape of ionics. So a lot of these properties are going to be ones that you're already familiar with. And why we talk about them is you should be able to use these properties to help you identify from a bunch of unknowns what kind of compound something is going to be. So when we think about metals, most of the time we're able to recognize a metal because metals definitely have very characteristic appearances to them, right? They tend to be gray and shiny. They're malleable and ductile, right? So we can bend them, we can stretch them into thin wires, we can reshape them. We find ionic compounds, they tend to have more of a crystal structure. They're very hard, they're very brittle. And the reason they're hard and brittle just has to do with the configuration of ions inside of those compounds, right? If you think about an ionic, we have positive charges and negative charges. And it's always going to be arranged so that the positives are surrounded by negatives, the negatives are surrounded by positives. And so part of why they're so brittle is if we knock this alignment off, right? So like if I had a big hunk of salt and I dropped it on the floor, you would find that it would knock these out of alignment and it would shift. So this positive would be next to that positive and that negative would be next to that negative. And now all of a sudden it's just going to shatter because we can't have like charges next to like charges, right? And we find that the malleability of metals, we can explain that using this C model that we talked about when we looked at the metallic bonds, right? Where we saw that the electrons were C moving around and all of those cations are kind of like the rocks. So we're able to reposition them because there isn't really a directional attraction like we have inside of an ionic compound. So that's why we find that metals will deform, right? We can bend them, we can stretch them, but they're generally not going to break unless we specifically break them. But ionic compounds will. If we are dealing with molecular compounds, the nonpolar ones can be solids, but they tend to be soft, right? Think of like a candle, right? It's waxy, so it's solid, but we're able to reshape it. You know, we can dent it to that type of thing. And that's because they only have London dispersion forces. Those forces are random, they change positions. So it makes it a little easier to move those molecules next to each other. Okay, when we start looking at moleculars that have more forces, right? So LDF, dipole-dipole hydrogen bonds, right? You can think of like sugar, right? Everyone's familiar with sugar crystals. Those tend to become a little bit more solid, a little bit more brittle, and they're a little bit more breakable or less breakable than those that are nonpolar. So to some extent, we can use the appearance to help us identify what type of compound we have. Just like with a network solid, right? I know what coal looks like, I know what graphite looks like, I know what diamond looks like, I know what glass looks like, and I know what sand looks like. So just by visually looking, a lot of the times I'm able to decide just based off appearance what type of compound it is that I have. In some cases, I can't though, right? If you think about salt and sugar, whenever I say this, you guys are always like, Ms. Chip, I know the difference between salt and sugar. I can tell the difference. But really, if you think about how you know the difference, usually it's because you taste them and they taste very different. But obviously, in a chemistry lab, we're not going to be tasting our different chemicals to try to help distinguish between them. So in some cases, we go to conductivity to help us decide that, right? And we've talked about conductivity back in the solutions unit. We talked about how to be able to conduct electricity, you had to have charges and they had to have the ability to move. So when you think about network solids and you think about metallics and ionics and moleculars, you're going to find that we can use conductivity to help us narrow down what they are. So in their solid forms, generally it's just going to be metals that have the ability to conduct electricity. If we had a nanotube, that would be able to conduct electricity, but high school chemistry lab, we don't have nanotubes, so we're not going to see any conduction of electricity. So most of the time, if we see that a solid is able to conduct, it's going to indicate to us that it's a metal. Now, is that super helpful? Not really, because most of the time we already know it's a metal just by looking at it. So where the conductivity becomes a little more helpful is in distinguishing between my ionic compounds and my molecular compounds, because a lot of times they look really similar, right? And if you think of salt and sugar, they look similar, right? They're both white crystals. They both dissolve in water, right? And they both dissolve in water because they're both polar molecules. And when we think about something being able to dissolve in something else, we generally talk about the generalization of like dissolves like. So that means water is able to dissolve other molecules that are polar. And that's because water is polar and those molecules are polar, right? And that's usually why you find if you have like an oil stain or a grease stain, it often doesn't come out in water because it doesn't dissolve in water. And so that's where you often take it to the dry cleaner, and they don't use water. They use different types of solvents that tend to be nonpolar. And so then they're able to get the oil out because the oil is going to dissolve into that nonpolar substance. But going back to the salt and the sugar, they both dissolve in water, right? And that's because a lot of ionic compounds dissolve in water, just like polar compounds dissolve in water. They're both white crystals on their own. So how can we distinguish between them? Well, we can check conductivity. We're going to find that because our ionic is going to dissociate in solution, right? And we talked about that back in the solution unit, it is going to conduct electricity. Whereas sugar is molecular, so even though it's going to dissolve, it's not going to form any charged ions in the solution. Because there is no charged species, it's not going to be able to conduct electricity. So I could use conductivity to help me decide between these two white solid crystals that look really similar to each other. Okay, the other time I'm going to find something is going to conduct, besides ionics in solutions, are going to be if I melt the ionic compound. Okay, if I melt an ionic, again, thinking back to when we talked about different states, right? We talked about how solid, we have our atoms in place, they're locked, they're not able to move, they're just kind of vibrating. Then we said we moved to a liquid and they had more energy, so they were able to kind of move around. They didn't have complete freedom like a gas, but they had the ability to break and reform those attractive forces. So what we also find is that ionics conduct as a liquid. Okay, and again, our moleculars aren't going to do that. So we can use conductivity to help us decide if something is a metal, because it's the only one that will conduct as a solid. And we can use conductivity to differentiate between an ionic and molecular compound, because even though they may both dissolve in water, we're going to find that it's only the ionic when dissolved in water that's going to be able to conduct electricity. Our molecular, when dissolved, is not going to conduct electricity. And so that's going to allow for us to distinguish between some of those solutions. And you're going to find that one of the last experiments we do in bonding is going to be to give you a bunch of unknowns and basically ask you to identify which ones are network solids, which are metals, which are ionics, and which are moleculars. And usually where you guys struggle the most is between the ionics and the moleculars, because they tend to look really similar, and you also sometimes make some generalizations that aren't always true, right? So this is where you have to remember that some ionics dissolve in water and some ionics don't. And what determines whether they do or don't is our solubility table. When we look at moleculars, some dissolve in water and some don't. And that's because some are polar and some are not polar. We can use conductivity, but the conductivity only helps us if our sample actually dissolves. But if we have an ionic and it doesn't dissolve, then checking the conductivity isn't going to tell us anything because our sample didn't actually dissolve into the solution. And so that's where another way that we can identify between an ionic and a molecular is going to be to do a melting test. So if you think back to when you were in Science 10, and I know some of you did this online last year, so you didn't really do this lab, but those of you who did it in first semester, remember we kind of took the aluminum foil on top of the spot plate, we kind of made those little wells, then we put our stuff inside and then we put it on the hot plate. Well, we can do that again here. And what we're going to find is that our moleculars are generally going to melt much faster than our ionics are going to. And so we're going to be able to use that melting point as well to help us differentiate if we're having a hard time deciding between two things. So besides being able to differentiate, we also need to talk a little bit about ionic crystals. So you will definitely find, and you should have noticed by now, that the majority of this unit we talk about kind of molecular compounds. We did a little bit on ionics on the very first day of the unit, then we kind of ignored them for the rest of the unit, and we spent all our time talking about moleculars. And that's why when you look at the weightings of the outcomes, you definitely find that moleculars are weighted significantly higher than ionics. So when it comes to our ionics, they do still have a three-dimensional shape, but their three-dimensional shapes are going to be very different. And that's because when we talk about ionics, although we might write the formula of NaCl for sodium chloride, that doesn't mean there's just one sodium ion and one chloride ion. It just means that the ratio of sodium to chlorine is going to be 1:1. So when we look at an actual ionic compound of sodium chloride, it's going to look like this, right? Where every chloride is surrounded by sodium and every sodium is surrounded by chloride ions. And the reason for that, like we've talked about before, is we always have to have positive next to negative. We can't put two negatives next to each other or two positives next to each other, right? You can also look at this more ball and stick model, which kind of spreads it out a little more, makes it a little easier to see. But again, you can see that all of the negatives are surrounded by positives and the positives by negatives. So you're never going to be asked to draw an ionic compound because obviously there's a lot of stuff going on in here. But we would definitely give you pictures and kind of ask you which one could be the correct representation, right? And really the biggest thing we're looking for is to make sure that our charges are properly aligned and we don't have positives next to positives or negatives next to negatives. So different ions you're going to find are going to kind of go into different types of crystal shapes. We don't get into crystal shapes. There's all kinds of different ones here. It talks a little bit about it, but we're never going to ask you that. I kind of briefly remember in one university course talking about how the charges led to different shapes and some were needles and some were cubes, but I don't really remember it that much. So obviously it wasn't something that we spent a lot of time on. Maybe if I took more courses on ionic compounds and crystal formation of them, I would know more, but I don't even remember the university offering those. So yeah. Biggest thing to recognize with those is just that positive next to the negative. And the fact that when we write those formulas, right, of NaCl or MgCl2, it's really just telling you what the ratio is. It doesn't actually mean that there's only 1 and 2 like a molecular formula does. When we're talking ionic formulas, we're just giving you the unit formula for it, which is the most simplified with respect to that ratio. So unit cells, again, we don't really talk about this. You don't need to know this for your unit test or anything, but it's just basically the smallest repeating pattern. And so if we were to cut down that large image to just the smallest repeating pattern, that's what we would get. We are not going to give you any pictures like that. The only pictures we are going to give you are going to be ones like these, where again, all we're going to ask for you to do is to be able to recognize which ones are possible and which ones are not possible, okay? So I want to say that is the end of bonding. That's going to conclude bonding. Unit test will be coming up shortly after this. You will have that one final lab that's going to cover identifying some unknowns. But yeah, that is our theory unit. So either you will have loved it or you will have absolutely hated it. Next unit that we're going to cover is going to be gases, and we're going to get back more into that math aspect. Still a little theory, but definitely not as much as bonding had. All right.